Welcome to another episode of GCSE Engineering Revision. Today we'll be going through 1.1.1, which is metals and alloys. Here's a snapshot of the specification, which will, as usual, be linked in the description. To start off, we'll go through a bit about metals and alloys and what ferrous and non-ferrous means. So what's the difference between a metal and an alloy? Well, metals are made of a single metal element, while alloys are made of a mixture of different elements. This makes alloys have enhanced properties such as corrosion resistance and greater strength. Some examples of metals include copper and aluminum, and some examples of alloys include brass, which is made of copper and zinc, and steel, which is made of iron, carbon, and chromium, amongst other things. Moving on to ferrous versus non-ferrous. The word ferrous comes from the Latin word for iron, which is ferrum. So ferrous simply means containing iron, and non-ferrous means not containing iron. It's as simple as that. Moving on to the comparative properties of metals and alloys. Just a small note before we get started. It probably won't be too helpful to memorize all these properties. So one thing you could do is memorize use cases for each material and work backwards to figure out a material's properties and how it can be applied to the real world. For example, we have copper. Copper is widely used in electrical wires. But why? Well, wires are used to conduct electricity, which suggests that copper is highly conductive. Furthermore, to be shaped into a wire, copper has to also be ductile. So, just from knowing that copper is used in electrical wires, we can tell that copper is highly conductive and also really ductile. Here's a quick summary of the relevant metals and alloys. We have whether or not they're ferrous, their relative toughness, hardness, strength, cost, and corrosion resistance. And we also have some special notes for certain metals and alloys. This should be taken with a huge grain of salt, as the ratings are arbitrary and should only be used to get a general idea of the relative stats of each metal or alloy. Let's take a closer look at cast iron. Cast iron has low toughness, it's very hard and very strong, and has a low cost. It also has poor corrosion resistance, which is why you usually see it being painted over. One thing about cast iron is, well, it can be cast, as its name suggests. This means it can be melted and poured into a mold to create a desired shape. It's commonly seen being used for pans and pots, and railings and fences, that sort of stuff. Next, we have low carbon steel. This is usually 0.05 to 0.3% carbon. It is very tough, quite hard, and quite strong, and it still has a relatively low cost. It is fairly corrosion resistant, and one thing about low carbon steel is that it cannot be hardened. It is used in a variety of car parts such as the suspension or the chassis, and it's also used in construction. Next, we have high carbon steel. This is usually 0.6 to 1% carbon. It is quite tough, very hard, very strong, and it has quite a high cost. It also has good corrosion resistance, and unlike its low carbon counterpart, it can be hardened. Since it's very hard, durable, and strong, it's used for stuff like drill bits and threaded fastenings. And it's also used for some construction applications and higher stress automotive parts such as shafts or gears. Moving on, we have stainless steel. This is very tough, very hard, very strong, and it's a very high cost. It is also very good corrosion resistance. This is the stuff you see every day in your pots and pans, and it's used in medical equipment and even eating and cooking utensils. Moving on to the non-ferrous metals, we have aluminum. Aluminum has low toughness, low hardness, and low strength when compared to steel. However, it has a high cost, although still lower than stainless steel. This is in part due to having very good corrosion resistance, which comes from a layer of oxide that forms on the surface of aluminum. Not only that, aluminum has low density, which gives it an exceptional strength to weight ratio, which is why it's used in airplanes and cars. It's also used in food packaging like soda cans. Next, we have copper, which has low toughness, low hardness, and low strength, but it has a high cost, even higher than aluminum, but still lower than stainless steel. It has exceptional corrosion resistance, even better than aluminum, and it is both ductile and electrically conductive, which is why it's used in electrical wiring, as mentioned earlier, and plumbing. Next, we have lead, which has low toughness, very low hardness, it's very soft, and low strength. But it has good corrosion resistance. It is also both ductile and malleable, but is toxic to human beings. As you can imagine, it's not as widely used as it once was. It used to be used in plumbing before they discovered it was toxic and killing people. Lead metal is now used sparingly, and one such use case is in solders, although you probably shouldn't be using lead containing solders. Finally, we have zinc. Zinc has a low toughness, low hardness, low strength, and all this for a low cost. It is fairly corrosion resistant, and it has a low melting point, so it is used for die casting. Zinc is widely used as a sacrificial metal or to galvanize a metal component. Also, since it can be cast, zinc and its alloys, brass and bronze, are used to make stuff with intricate shapes, such as door handles. Next, we'll talk about some heat and chemical treatment processes. First, we have normalizing. Normalizing is done on steel that has been work hardened. And we do this by heating it above its upper critical point and leaving it to cool in air. The result is a tough and ductile metal that is easy to machine. Similarly, we have annealing, and this is done on metal that has been work hardened. We do this by heating it to a suitable temperature and leaving it to soak at that temperature. The result is a soft and easy to work with piece of metal. So what's the difference between normalizing and annealing? Well, annealing can be done on any metal, and it cools slowly in the furnace. The result is a softer and more ductile piece of metal. Whereas normalizing is for steel only, and it cools faster in air. This results in a finer grain structure that is stronger. Moving on to hardening and quenching. This is done on high carbon steel only, and we do it by heating it above its lower critical point and then leaving it to soak at that temperature. This gives it an austenite structure, which is ductile and formable. It can be easily shaped. Then we quench it. We immerse it in oil or brine. And brine is kind of like salt water. This results in a martensite structure, which is very hard and brittle. Finally, we have tempering, which is done on martensitic steel, which, if you can recall, is what hardening and quenching gives us. To do this, we heat the metal to 230 to 300 degrees Celsius, and then we quench it. This results in a less hard and less brittle, but tougher piece of metal. And as mentioned, it's usually done after hardening and quenching. That's about it for today. As usual, the slides will be linked in the description. Thank you for watching.